Geometry is the study of shapes. We all studied this in school. The simplest geometric objects are things defined by a polynomial, x squared plus y squared equals 1, and so on. Then you get up to dimension 3, it could be threefold, and there the main issue of it was, can it be parameterized in the same way that, for example, you parameterize a circle by projecting stereographically onto a line?
The question explicitly goes back to the 1960s. So there's a very famous work of Clemens and Griffiths about the threefold version. And it was one of the most celebrated proofs in algebraic geometry in the 60s.
That proved irrationality in contrast with the dimension 2 case.
And there's sort of the obvious question to try to go forward and do the fourfold case.
And in dimension 4, so there are some tools from Hodge theory where people try to believe or to mimic that has been proved not to work.
And since then, there really hasn't been that much progress in the field until quite recently the theory of atoms was developed. So Ludmil and Tony and Maxime, they were able to solve the analogous problem in 4 dimensions. So whereas Clemens and Griffiths showed that the cubic threefold was not rational.
Defining something of dimension 4, then it cannot be parameterized in the same way that a line parameterizes a circle. There is no stereographic projection.
As far as I understand, it's one of oldest unsolved problems in birational geometry for 80 years. Many people broke their teeth. It shows the force of the new methods here.
People in birational geometry have been trying to solve this problem for 50 or 60 years and unsuccessfully until now. So
now they're able to prove it in 4 dimensions, which is a major step.
Just mentioned the proof was based on ideas arising from mathematical physics, from string theory. It's the first time that those tools that I'm aware of have really been brought to bear on an old classical geometry problem that had defied all attempts to get at the answer by traditional methods.
More interesting for me than the result is the fact that it uses ideas, not necessarily like logically, but is inspired by by mirror symmetry, which has sort of been its own field that's been trying to understand these ideas of physics. But this is the first case where a really classical problem, where it's been applied to classical problems. And I think it's the start of these techniques in mirror symmetry becoming even more like quantum cohomology, becoming even more like fundamental invariants in algebraic geometry.
The proof is quite amazing here. I have to say, it's kind of really out of this world in a sense. It's used very different tools which people never thought.
So it's really connecting back to basic questions in math. That's maybe the most interesting part of it for me.
But the more general question about what is really the general other sorts of applications, I don't know. I don't know, but I am sure that something new is going to be developed using these ideas. Because, as I said, when you put together two theories, Hodge theory, Gromov-Wheeler theory, you do something spectacular with that. It's very clear that people will want to continue, find maybe other types of applications.
There could be more applications if we were able to prove certain fundamental facts about quantum cohomology. So somehow now, I think that now it's going to get more people involved in the theory of quantum cohomology and trying to really develop these deeper properties that would have applications. So I think that's sort of the direction.
It's definitely opened some new perspective in low dimensions. traditional use of Varolgunes geometry, we can overcome the dimension barrier.